Welcome to the deep dive. Today, we're jumping into something pretty technical, signal processing, but we're going to break it down.
Yeah, specifically filter mechanics. Our goal, really, is to get super clear on two key ideas, phase delay and group delay. And crucially, why knowing the difference matters so much when you're designing filters, especially those FIR, finite impulse response types.
Exactly. It sounds abstract, but it's fundamental.
Think about it this way. You put a signal through a filter, maybe music, maybe, I don't know, radio waves. The filter adds a delay. But the big question is, does it delay everything the same amount? Or does it kind of warp the timing?
Right. If different frequency parts of your signal get delayed differently, you get distortion. The message, the information can get scrambled.
So we need the right tools, the right concepts, to actually measure that timing distortion. Simple delay isn't quite enough. No, it's not, because signals are complex. They're made of lots of frequencies working together. And we need to know, well, two things. How much is the individual frequency tone delayed? And how much is the information delayed, the pattern carried by those frequencies?
Okay, got it. Let's tackle the first one then. Phase delay. This sounds a bit simpler.
It is, conceptually. Phase delay, sometimes just called time delay, is basically the time shift for a single pure tone.
Like if I send just a 1 kilohertz sine wave through the filter.
Exactly, that specific 1 kilohertz tone. The phase delay tells you how much that individual component is shifted in time by the filter. It comes down to the phase shift the filter introduces at that specific frequency.
So mathematically, it's related to the filter's phase response at that frequency, divided by the frequency itself.
Precisely. It's the negative of the phase shift, let's call it theta, divided by the angular frequency omega. So tau equals minus theta over omega.
Okay, so phase delay, time shift for one specific frequency component. Simple enough.
Right. But now, let's get to group delay. This is often, well, more critical for real-world signals, the ones carrying information.
Okay, group delay. Now, intuitively, I might think that's just like the average delay for all the frequencies. Is that right?
Not quite. It's a bit more subtle and actually more powerful than that. Group delay measures the time delay of the envelope of the signal.
The envelope.
Yeah, think of a pulse or a burst of data or the modulation on a carrier wave, that overall shape, the pattern. Group delay tells you how long it takes for that envelope, that group of frequencies carrying the information, to pass through the filter.
Okay, so not the individual waves, but the shape of the wave packet.
You got it. And this is where the math gets interesting. It's defined differently. Group delay is the negative derivative of the phase response with respect to frequency. So tau g equals minus d theta by d omega.
A derivative. Okay, hold on. So phase delay uses the phase value itself, but group delay uses how fast the phase is changing as frequency changes.
Exactly. That derivative captures the slope of the phase response curve.
Why is that slope so important for the envelope's delay?
Because the envelope is formed by the interaction, the interference pattern of frequencies that are very close together. The way those closely spaced frequencies interfere depends critically on the difference in their phase shifts. And the derivative tells you exactly how rapidly the phase changes between adjacent frequencies.
I see. So, summing up, phase delay is about the carrier tone's timing, group delay is about the information's timing, the envelope.
That's the core difference. One tracks the wave, the other tracks the message on the wave.
But hang on, if phase delay is simpler to calculate, why isn't it good enough? Why do we need this more complex group delay concept to measure distortion?
Great question. It comes down to something called dispersion. Basically, different frequencies traveling at different speeds through the filter.
Okay.
Imagine sending a short, sharp pulse like digital data or radar. That pulse isn't just one frequency, it's made of a group of frequencies. Now, if the group delay isn't constant across that group of frequencies,
meaning the derivative, the slope of the phase response, is changing.
Precisely. If that slope changes, it means the different frequency components making up your sharp pulse are effectively traveling at different speeds through the filter.
Ah, so some parts of the pulse arrive sooner or later than others.
Exactly.
Right.
The lower frequency parts might get through slightly faster, the higher frequency parts slightly slower, or vice versa. What happens to your nice sharp pulse? It gets smeared out, elongated, the sharp edges become fuzzy.
That's the distortion, the smearing of the envelope.
That's phase distortion, yes. And group delay is the metric that directly measures this smearing potential. If group delay varies with frequency, you will get this kind of distortion.
So for anything where the shape of the signal matters, audio, video, data transmission, radar group delay is king.
Absolutely. Constant group delay means all parts of the envelope arrive together. The shape is preserved, Variable group delay means the shape gets distorted.
Okay, this makes a lot more sense now. We care less about the absolute arrival time of a single sine wave, and much more about keeping the whole information packet arriving coherently. All right, let's apply this. FIR filters, finite impulse response filters. These are often the go-to for high-fidelity stuff, precisely because they handle these delays really well, right?
They can, yes. They offer designers a lot of control, especially over the phase response. And the ideal we usually strive for in high-fidelity applications is what's called a linear phase response.
Linear phase. Okay, that sounds like, well, a straight line.
It is. It means the phase shift introduced by the filter is directly proportional to the frequency. Double the frequency, you double the phase shift. Plot phase versus frequency, and you get a nice straight line.
And why is that straight line, that linear relationship, so desirable?
Because of what it implies for our two delay types, especially group delay.
Back to the derivative. If the phase response is a straight line,
What's the derivative of a straight line?
it's constant. The slope is the same everywhere.
Exactly. So if you have a linear phase filter, the group delay, the negative derivative, is constant across all frequencies in the passband.
Meaning all parts of the signal envelope, all those groups of frequencies, are delayed by the exact same amount of time?
Correct. No smearing, no phase distortion. The envelope shape is perfectly preserved, just shifted in time.
Okay, constant group delay. That's the big win for linear phase. What about the phase delay in that case? Is it also constant?
This is where it can seem a little counterintuitive at first glance, but let's walk through it. Phase delay, remember, is minus phase divided by frequency. If the phase itself, phase omega, is increasing linearly with frequency, let's say it makes C divided by omega, where C is a constant representing the slope, then the phase delay is.
Minus C omega divided by omega, which just equals C. It's constant too.
Right. In a true linear phase filter, where the line passes through the origin or has a specific phase offset, both the group delay and the phase delay are constant, and, importantly, they're equal to each other.
So wait, I thought the outline mentioned phase delay ramping linearly in some cases. Let's clarify this, because some sources differentiate between constant phase and linear phase.
Good point. There's a nuance often tied to how people define linear phase, or if they consider phase offsets. Let's be precise. The most common and desirable type of FIR filter for preserving waveforms is one with a symmetric impulse response. This symmetry guarantees a constant group delay.
Okay, constant group delay is guaranteed by symmetry.
Yes. Now, the phase response itself for these symmetric FIR filters is linear, but it might have an intercept. It looks like theta omega, alpha tau omega. Here, tau is the constant group delay.
Alpha, what's that?
Alpha is a constant phase offset, often 0 or PM pi 2, depending on the symmetry type and filter order. The key part is the tau omega term, which is linear.
Okay, so the phase is linear. What does that alpha term do to the phase delay calculation?
Let's see. Phase delay, alpha tau omega.
So the phase delay isn't perfectly constant if alpha isn't 0. It's the constant group delay value plus a term that varies with frequency.
Alpha omega.
Exactly. So for the most common type of linear phase FIR filter, type I, symmetric, odd length, alpha is 0, and both group delay and phase delay are constant and equal to little l1 to 2, where n is the filter length.
Okay, so in that common case, they are both constant.
Yes. But for other symmetry types, like type 2, 3, 4, alpha might not be 0. In those cases, group delay is still constant, which is the critical property for avoiding envelope distortion. The phase delay, however, might have that $1 omega dependence because of the alpha term.
I think I'm getting it. The defining characteristic of these useful FIR filters is the constant group delay, achieved because the phase response is fundamentally linear, even with a possible offset. Whether the phase delay is also perfectly flat depends on that offset term, alpha.
You've nailed it. Constant group delay is the prize we're after for signal fidelity. The linear phase response, guaranteed by symmetry, delivers that constant group delay. And how do we actually design filters like this? You mentioned symmetry.
Right. The impulse response of the filter, the coefficients, needs to be symmetric or anti-symmetric around its center point. And algorithms like the Parks-McClellan algorithm or Rembes exchange are commonly used to design FIR filters that approximate this ideal linear phase response very closely while meeting frequency magnitude specifications.
Okay, let's use that example from the source material to really lock this in. Two frequencies, F1 and F2, where F2 is double F1.
Right. If you pass both through a filter with constant group delay, i.e. linear phase, the relative timing between them is preserved. Even if the absolute phase shift for F2 is double that of F1 because the phase is linear, the difference in their arrival times, related to the envelope they might form, is maintained because the slope of that phase response, the group delay, is constant.
So the constant derivative keeps their relationship intact, even if higher frequencies experience a larger absolute phase shift.
Precisely.
And just to be clear, if we didn't have that linear phase, if the phase response curve was, well, curvy,
Then the derivative, the group delay, would change with frequency. You'd get dispersion, smearing, distortion.
which happens with lots of other filter types, right? Like analog filters or IR filters sometimes.
Often, yes. While you can design IR filters to have approximately linear phase in the passband, it's much harder and often involves compromises. Achieving truly constant group delay is a natural strength of symmetric FIR filters.
That's why they're so valued in audio, image processing, datacomms.
Yeah.
Anywhere preserving the waveform shape is critical.
Exactly. You need that constant group delay.
Okay, let's try and wrap this up. Key takeaways from this deep dive. Phase delay tells you the time shift for a single frequency tone, calculated from the phase value itself.
And group delay tells you the time shift for the signal's envelope, the information packet. Crucially, it's calculated from the derivative of the phase response. This is the key metric for phase distortion.
And for FIR filters, the gold standard is linear phase, which we achieve through symmetric impulse responses.
Right. And that linear phase characteristic guarantees a constant group delay across the frequencies we care about.
Which means minimal distortion, the signal shape is preserved, just delayed uniformly.
Perfect summary. Understanding that link between the phase response shape, its derivative, group delay, and the resulting signal integrity is, well, fundamental for good filter design.
So connecting this to the bigger picture for listeners, choosing between filter types often comes down to understanding if constant group delay is essential for your application. Audio? Video? Probably yes. Some control systems may be less critical.
Precisely. It dictates your design choice. But here's something to chew on, a final thought.
Go on.
We have established that linear phase FIR filters, with their constant group delay, are fantastic for preserving signal shape. They offer near-perfect phase fidelity.
Right, the ideal scenario.
But there's no free lunch in engineering, right? What's the cost of achieving that perfect linear phase via impulse response symmetry?
I guess designing them might be complex.
That, but more fundamentally, achieving that symmetry and often sharp frequency cutoff requires a relatively long impulse response, many filter coefficients or taps.
And a longer filter means?
More calculations, more processing power, and, critically, more latency. The constant group delay itself, while uniform, is often significantly larger than the delay you might get from other filter types like IIR filters.
Oh, so the filter that gives you the best phase performance, the least distortion, often introduces the most overall delay.
Exactly. The group delay value, TOC, which is constant, represents the actual time lag the entire signal envelope experiences. For a symmetric FIR filter of length n, that delay is typically due to Sokal samples. Longer n means better frequency selectivity or smoother phase, but also means larger delay.
So you have this trade-off. Do you prioritize perfect waveform fidelity, accepting a potentially significant delay? Or do you need lower latency, near real-time processing, even if it means accepting some phase distortion from maybe an IIR filter or a nonlinear phase FIR?
That's the core engineering decision you often face. Which is more critical for your specific system? Minimizing phase distortion or minimizing overall latency? Something to think about.